Here we've got a limit that we're asked to evaluate. We let x go to infinity, and we want to know what happens to this function. Well, let's look at what happens to each part. So as x goes to infinity, obviously that first factor there is going to infinity. And then as x goes to infinity, here we have 1 over x, so that part's going to 0. And we know that sine, if what is inside the sine function is going to 0, well, sine will go to 0. So that second part is going to 0. That's not an indeterminate form that L'Hopital's rule applies to. It's not a 0 over 0 or infinity over infinity, but it is an indeterminate form. Let's take a look at that situation. What if I get 0 times infinity from a product like I'm getting in this particular example? Well, let's analyze what happens. So in this product, if I have one of the factors going to infinity, then obviously that's trying to make the product infinite. If one of the factors is growing huge or negative, depending on whether the other factor is negative or whatever, but if it's growing to some sort of infinity, it's trying to make the product infinite. Likewise, if the second part is going to 0, the other factor is trying to take it to 0, then that's trying to make the product 0. So this is indeterminate. They're pulling in different directions. One's trying to pull to infinity, one's trying to pull to 0, and we can't determine what's happening in that situation. And that's true over here too, even though that's not the case for this one, but this is another indeterminate form. If I have a difference and the first term in that difference is infinite, is heading towards infinity, then it's trying to make the whole difference infinite, right? A huge number minus something is trying to be huge. But then what if the second number is also becoming huge? Is subtracting a huge number. That's trying to make the whole thing negatively infinite. This one's trying to make it positively infinite. Well, they're pulling in opposite directions. This one's trying to pull it to positive infinity. This one's trying to pull it to negative infinity. That's indeterminate. There's lots of indeterminate forms, but these are the two I want to focus on here. These are the indeterminate forms in which L'Hopital's rule cannot be applied, unfortunately. Not as they stand. The L'Hopital's rule requires 0 over 0 or infinity over infinity, plus or minus here. So you can't forget that. But that doesn't mean we can't manipulate this into those forms. And so the way we do it is just anytime I have a 0 times infinity, I can take the infinity and algebraically think of flipping it over into the denominator. When you flip it over into the denominator, it becomes that. Now, obviously, infinity is not a number, but whatever's turning into that infinity can be flipped over. And that part's now going to 0 and 0. Or I can flip the 0 over. I've got this infinity. If I flip the thing that's giving me 0 over, that's infinity. But remember, this is going to infinity. So I can convert it to either of these forms very easily by flipping one of these over into the denominator. So this is going to be the limit as x approaches infinity. Well, you flip the one that's easiest. I don't want to flip 1 over sine. I want to flip x. I don't want to flip sine and make it 1 over sine. The x is going to be the easier one. So this is equivalent to, because how would I get this back out of the denominator? I'd flip it back out. So I can flip it in or flip it out. Now what I've really done is I've multiplied by 1 over x and the bottom by 1 over x. So you can think of this as being a fraction, and then that 1 over x cancels in the top and the 1 over x ends up in the bottom. But it's just as easy. If we always remember, flip the bottom and multiply, but you can also take what's a factor of the top and flip it back into the bottom, flip it over and put it in the bottom. And now we already checked sine of as x goes to infinity, this is going to 0 and this is going to 0. So now I have a form that I can apply L'Hopital's rule to. This is going to be the limit as x goes to infinity. Let's start in the bottom. Derivative of 1 over x is minus 1 over x squared. The derivative sine of 1 over x is the derivative sine. Put the 1 over x back in. Using the chain rule, you get then minus 1 over x squared. That cancels out nicely so that I end up with just the limit as x goes to infinity of cosine 1 over x. And cosine 1 over x goes to cosine of 0, which is 1. So this original limit is 1. So neither one of them is winning. It's not getting pulled to infinity. It's not getting pulled to 0. It actually ends up somewhere in between at 1. So I'm going to work a few more examples of both these indeterminate forms. The one we run into a lot is this 0 times infinity form. So here we've got natural log times tangent, and I'm trying to take the limit as x goes to 0. Remember your natural log graph. As I'm coming into 0, natural log is going to minus infinity. And tangent, your tangent graph, something like that. But as I'm coming into 0 from this side, it's going to 0. So I get an infinity times 0 form, which is indeterminate. And I know that all I have to do is flip one of these over and put it in the denominator. Do you want a 1 over natural log of x in the denominator, or 1 over a tangent? Probably a 1 over tangent, because that has a name and we know how to take the derivative of that thing. So I'm going to flip that one into the denominator. Take the limit as x goes to 0. I'll still have my natural log. And now I've got a 1 over tangent. But like I said, that has a name. That's cotangent. So this is the limit as x goes to 0. Natural log of x over cotangent x. And if I did my analysis right here, I already know that's going to infinity, and this will go to infinity. Even if you don't remember what the graph looks like, you can think of it as being cosine over sine, and that puts a sine in the denominator, here in the denominator, but you get a 0 in that denominator, which will go to infinity. We'll cause that fraction to go to infinity. But now I can use L'Hopital's rule. Derivative of the top, derivative of natural log of x is 1 over x. Derivative of cotangent is minus cosecant squared. And I'll do the algebra that's allowed here, which is this. I'll flip this fraction over, and what I end up with is the limit as x goes to 0 of 1 over, there's a minus, I'll put it out in front, x cosecant squared x. As x goes to 0, I've got cosecant squared, which is 1 over sine squared. And so I end up with 1 in the top. In the bottom, I'm going to have going to 0, and then cosecant, well, that's actually going to infinity. So I kind of get a 0 times infinity in the bottom. So it's telling me, take this cosecant squared, turn it into 1 over sine squared, and flip it back to the top. So this is really x times 1 over sine squared in the bottom. So that limit's going to become the limit as x goes to 0. There's a minus. That sine squared is going to flip up to the top now, and that's divided by x. And now I can apply L'Hopital's rule to that, because as x goes to 0, both of these are going to 0. I'm going to say this is the limit as x goes to 0 from the right. I get minus. The derivative of the top is going to be, get a little bit of room here. You're going to get 2 times sine, because this is sine squared, so you're taking a derivative of the outside function. That's 2 times sine, and then the derivative of sine, which is cosine. And the derivative in the bottom is 1. So I no longer have a 0 in the denominator, and I can see that then I can now evaluate this. The bottom is 1. The top is going to be sine of 0, cosine of 0. So that's 2 times 0 times 1. So that's going to be 0. So this original limit does go to 0, which in some sense says the tangent won this competition. It actually pulled it to 0. All right, let's do this one that's got a difference involved. You've got x going to pi over 2 from the left. So you have to know something about secant. Secant is 1 over cosine, and cosine looks like this. And so if you're approaching pi over 2, which is where cosine is 0, you are going to get an infinity. And since I'm coming from this side, you're going to get a positive infinity. So you do have to get the sign right on this. It needs to be positive or negative infinity. So I'm coming from here, I'm going to be putting positive numbers in. Tangent, we know what that graph looks like, so we can do that one without referring back to sines and cosines. As I'm coming to pi over 2 from this side, I'm also getting infinity, but I'm subtracting it, so I do get an infinity minus infinity. Well, the way you typically handle these is you try to combine them into a single fraction, and I can do that by converting to sines and cosines. So this is the limit as x goes to pi over 2 from the left. I get 1 over cosine and sine over cosine. Well, those combine naturally because they already have a common denominator. So that's going to be the limit as x approaches pi over 2 from the left of 1 minus sine over cosine. And then if I check what happens here, sine of pi over 2 is 1, so I get 1 minus 1, top's going to 0. Cosine, as we said, at pi over 2 is 0. So I do get my indeterminate form that I can now apply L'Hopital's rule to. So this is going to be the limit as x goes to pi over 2 from the left. Taking the derivative in the top, the derivative of sine is cosine, but there's already a minus sign there, so it's going to be minus cosine. Derivative at the bottom, you get minus sine. And as x goes to pi over 2, the bottom goes to 1, and the top is 0. So I'm going to go ahead and say equal because I can calculate that. There's no 0 in the denominator, which means I do get 0 from this. Which says neither one is winning. It's somehow they are sort of canceling out, but don't look at this saying, oh, well, infinity minus infinity is 0. That's indeterminate. It just turns out the limit as x goes to pi over 2 of this combination, even though it has this indeterminate form, that does end up at 0 when you take that limit.